Today we are going to talk about resilient system and how to design or practice some best practices in distributed systems so that we can detect uh, failures gracefully and handle failures gracefully. So about me, as Swapnil mentioned, I am a senior software engineer working for Adobe in their cloud technology and Sensei group. And I'm a contributor to 20 plus open source project, including Hystrix Servo, Contour, and Spinnaker, open tracing lately a lot in, and Istio as well. I run Java user group also. So if you have any topics to present, you can reach out to me. I am based out of Sunnyvale, and I usually you can find me in a lot of conferences. I have shared my GitHub and Twitter as well. So if you have any questions which we are not able to answer in this session, you can always reach out to me on Twitter, and I'll be happy to answer any questions. So that's about me. Let's start. So distributed architecture or distributed system. So like we all so what happened is in the distributed architecture, you are distributing your system and components over the internet to do the resource sharing, to do computation. Because what happened was earlier, you had all these systems which were monolith. And now with the evolution of cloud, with the evolution of distributed computing, people have started distributing their load into different servers in order to do the computing faster, in order to share the resource, in order to use the resources efficiently. So basically, these diagrams represent your microservice architecture, where these are some of the traits for your microservices. Microservices word is again an example of distributed computing, because essentially you break down a bigger system into separate individual components, and then each component is responsible for a particular functionality. And now you deploy those components separately, and then you perform the computing and things like that. So each of the component, it becomes a microservice, and it is responsible for a particular functionality. Take an example of Uber. So in Uber, say you have components like payment, you have components like ride sharing, you have components like ride booking, customer management. So all these components become microservices, and essentially you can break them further if they are too heavy. But the core idea behind that is you are breaking your component into a different system, and each of these systems have a separate life cycle. So that is why we saw the evolution of CI/CD, continuous integration and deployment, and things like that. So you want to manage their life cycle. Now, one of the philosophy behind the microservice architecture was they are heterogeneous in nature. That is, you are free to choose your own technology. So, for example, in one microservice, you can use Java as a programming language. Then in another, you can use Go as a programming language. So you have some freedom on technology selection. And then the resources are distributed, and essentially multipass involves where in order to work all these microservices or distributed systems, they have to have some kind of coordination. So coordination, it means they have to talk to each other. And that is where the different design patterns come into picture. So since they are talking as a separate resource, so you need to have some kind of control over there, what kind of authentication and authorizations are there. So then essentially, because you have distributed your load, so your one microservice can reside anywhere, your another component is residing anywhere, but they are talking over the internet or over the network. So that is why the computation is distributed. But again, this is all fine and dandy, this is all good, but what happens here when any of the component fails? Now, suppose because these components are distributed, and if you have to debug which component is behaving badly, what is the reasoning behind that, then it becomes a challenge. And that is why you can't see. So that is why you see this guy is saying, I don't see the problem. Because there are certain traits you need to follow. There are certain best practices you need to to follow if you want to debug the problem quickly, because problem can be anywhere. Network is a fallacy, so network can go wrong, or any component can behave badly, or there could be things like load of one component is choking another component. So there could be n number of problems go wrong in the distributed systems. So this is the other aspect of distributed system architecture, where if you are not careful, then bad behavior of one system can go wrong and take down the entire system, which goes against the philosophy of distributed system as well as microservices as well, where essentially they were meant to be designed to be operating independently. So it means you, while designing your system, you should be careful about certain traits where the dependency, they are loosely coupled, they are not strongly coupled, so that you can replace them, you can manage their life cycle, as well as bad behavior of one cycle, one's component does not affect the another component. So, and then this is what happens. If system starts behaving badly, you don't have any idea where the things are going wrong. This is what happens. This is a meme from Avengers, where Spider-Man is saying, I don't feel good, and I don't know what is happening. So essentially, you need to figure out which component is behaving badly. So this is the problem statement, like how we can see what all practices we should do, so that if any problem arises in the distributed system architecture, we can detect it quickly, we can isolate it, and we can resolve it. Because in order to resolve the problem, you need to detect it first, which component is behaving badly, and can you replace it? Can you replace it from the system? So, or can you stop the flow? Can you isolate that component so that it does not affect the entire system, right? So let's talk about that. So here, when we think from the problem perspective, what problem can we see? So first of all, we need enough information as in where the things are going wrong, what things are going bad. So in order to know that, you need to have enough contextual information. You need to have enough information about through logs, through different kind of components. You need to have the context. You need visibility as in, if these microservices or distributed systems, they are talking to each other, you need to know where the integration is failing, where the component is failing. So you need to have that kind of visibility, so that you know, you can quickly debug which system it needs to, which system you needs to focus on. You need to be able to stop the bad component or isolate the bad component as soon as possible, because with the evolution of cloud computing, you have the ability to scale your components up and down, horizontally or vertically, right? So if you can isolate that component, you can quickly spin up another component which can take place of the bad component. But you need to first identify which component is bad, and then you need to find it out, and you need to have some sort of control, like how you should be dealing with that bad guy. So around these four categories, let's talk about what we can do. So because we talked about we need enough information, so enough information means you need to have the logger. Now, traditionally, the logging has been, what we do is we generate the logging statement, we print it in a file or somewhere, and then we use some sort of log retrieval or log parsing tool like Splunk to generate some meaning. And then if in case of any failure, we rely on our logging. So traditionally, this logging is in the plain text format. Now, what we can do is, and what I have done is, there is this concept of structured logging. Now, what structured logging is, with your logger, you are appending the contextual metadata with the logging. So you can, what does that mean is, in case of any problem, you can attach extra information with your logger in a form of JSON payload, as you can see in the example here. Which tells you which you can associate like user, which you can through which you can associate metadata information from your logger. For example, is it a customer flow? Is it a golden flow? Is it a what kind of matrix it is, and where this exception is coming? So that way you can add the contextual information. For example, in this snapshot, if you see, this is saying action is repair and thing is car. So now if we interpret this, if the logging system interpret this, and if a user sees this, they can quickly know, like apart from the log name, this is where the additional system information is. Think from perspective in distributed system, your log are pouring into from different systems into a central logging place. And anytime something happens, you need to find like, hey, where the things are going wrong. So that is why you need to have associate the additional contextual information here. Now, this is a relatively new concept, but what happens is because right now not all logging systems are supporting this kind of logging, but then you have ability to write your own log parser, especially in the Fluentd or in Splunk. They started supporting it. So you need to give the schema, because you can implement a standard schema or a particular schema, custom schema, but you need to tell your log parsing tool like how to parse this information, how to process this information. So that way you can write it down. That way you can see it, you can parse it in the relevant format. And that way you can quickly detect, you can associate metadata information also with your log. Common format. This is another problem we see, because as the organization or teams or components grow, we have a disjoint set of logging format and things like that. So what happens is you need to have some kind of common logging format, some kind of governance there. For example, you can generate all the, say in Splunk word, you can generate the index as commonly formatted, like application name dot something name. And then in the logging also, you can print out like method name and all those. So that way there is a governance and uniformity. And this especially brings down if you try to think in terms of SRE terminology, so this significantly brings down the MTTR, mean time to repair. Because every time when you try to debug something into, say, Splunk, and now you have to find the appropriate logger. And if you are not aware, you cannot find the index name, you cannot find the log name, and you cannot debug the problem. So that way you need to find, if we have a common formatted loggers, you have uniformity there, and then you can quickly find the logger name, and then you can quickly debug the information. So that is how you, this all focuses on the efficient logging. So now we talked about logging information. So we have the information, but now we need to find out how the flow works, how the things are working in. So in this case, you need to get some visibility onto where your calls are going. If you have different components talking, how are they talking? So if you have this kind of information, then you can quickly detect, like, hey, at this level, your call is failing. So for this phenomenon, we have this concept of observability. So observability is essentially talking about two things. So one is distributed tracing. So especially in the microservice world, what you need, this concept tells you, you propagate a common set of headers across your different calls. Now what happens is you have service A calling to service B, calling to service C in a user flow. Now you are propagating a common set of headers across these calls. And then if you have to retrieve the information for a particular user, you can retrieve by those headers. You can pass the customer ID or user ID or whatever information you want to pass up. But there also goes some kind of decision making, because you need to identify how you want to group your flows, how you want to see. So for example, in this snapshot, if you can see, there is this hello client is calling the formatter, and then publisher, echo tracer. So this is showing you the spans and traces, like how much each call is taking. and how much time each call is taking, and then essentially when you build your timeline, like in a timeline, uh, how it is rolling up to the entire call stack. Second concept is the call graph tracing. So call graph is again a concept of tracing, like when you are talking in a microservice world, when one service is talking to another and things like that. So call graph tracing comes into picture when you have to trace the flow. So you have to trace, for example, in Uber's world, again, if we go back to the Uber, you are booking a ride, but behind the scenes, there are a lot of things happening. It is finding the available number of rides. It is when you're trying to book, it is calculating the distance, it is calculating the price. So there are different microservices or different functionalities working together. Now, if you have to trace it, like when user clicks on book a ride, what all things happening there. So that is where the call graphs comes into picture. It is a way to visualize how your microservices are talking to each other. So that is how call graph works. So again, in order to trace this, in order to visualize this, you have different mechanisms. You can leverage distributed tracing again to pass that header, and you can quickly visualize. There are tools like Kiali where you can visualize these call graphs. Or even in this case, this snapshot is from Jaeger. Jaeger is again a distributed tracing library from Uber. So that gives you this kind of instrumentation, which you can instrument in your code, and then you can quickly generate your call graphs. So you can identify where your call is going. So that is how you identify the patterns, like where your call is going. So logger gives you the contextual information, and then the call graphs give you information about the communication. Control switches. So we talked about, so we have information like what kind of contextual information. We have the visibility through tracing. And then once we identify the component, how do we stop the flow? So that is where the control switches and bounded architectural contexts come into picture. Because using control switches and bounded architectural contexts, you can stop the flow. Now, what does this mean? So there are two kind of architectural contexts you need to decide. So in a distributed system, like we talked about, if two systems are talking and one system is behaving badly, you should always have a means to disconnect that system. Now, what does that mean? You need to be aware about your participant systems in what all systems are working, what all components are working in a system, knowing the limits. So when you are integrating with any system, when you are talking to any system, you should be knowing what their system boundaries are, whether they can scale to a particular limit or not. And then if they can't, then you should always have a throttling kind of mechanism. So throttling mechanism is like you can always stop the flow from going there. You can hold the request till the time other system recovers. So usually for throttling, in different people uses a queuing kind of mechanism, where they hold on the request and then they apply the leaky bucket algorithm. They only pass the number of requests which can be handled by downstream systems. But again, this is a best practice you should always implement, where you can hold the request and process it as per the downstream system's capacity, so that you don't end up choking. Or even if the downstream system is behaving badly, you can stop the flow there. Controlled blast radius. Now, this essentially these blast radius terminology is used in terms of distributed system. When any system goes wrong, how quickly you can stop the domino effect so that it does not propagate to other components in the system. So that is how when you need to control the blast radius, you need to isolate that component again, the faulty component again. And now in this case, feature flags are one of the methodologies adopted by different companies and teams. So whenever you are integrating with any other dependency or any other system, whenever you are talking to any other system, you can always enable it or disable it based on some flagging mechanism. So that is how the feature flagging come into picture. And feature flagging is also used for gradually controlling the interaction as well. So same concept, if you want to apply some kind of, you want to release some kind of feature for certain set of users or things like that, there also feature flags being used. But again, if you want to apply feature flags in terms of infrastructure, you can also use there to quickly stop the flow or quickly isolate a particular component. Circuit breaker. So circuit breaker is a design pattern which gives you the ability to define the fallback behavior at the runtime. And now there are different libraries where you can do this on the code side. And now there are infrastructure component as well, which gives you this kind of ability. So essentially what happens is if you're talking to any system and that system starts behaving badly, then you can actually define your fallback behavior and you can define a chain of fallbacks. For example, in a real world system, if say you are developing an application where you are trying to fetch the codes of the part, like if you are in a repair kind of system where your customer comes in, submits the device, and then you quote their repair cost and things like that. So in that case, you need to fetch the inventory from some system, and then you need to get the pricing information, quote information, things like that. Now, these things are critical for the application. But what if say you are fetching this information from a third-party site, and that site goes down? What are your options? Because you cannot stop the customer flow. So you need to find a way where you can handle this failure gracefully. So maybe you can develop a system which syncs with the third party, and then you can at least give a code to customer. So now, how do you handle this? So circuit breaker design pattern helps in these kind of failure scenarios where if the third party goes down, it automatically enables a fallback behavior, and in fallback behavior, you can define how the alternate flow look like. And it also gives you the ability to define. It also gives you the ability to define a chain of fallbacks, where if one component goes down, you can rely on the second flow. If second goes down, you can rely on third, and so on. So that is how the circuit breaker helps. Now we talked about circuit breaker design pattern. So there are two places where you can implement the circuit breaker design pattern. One is via code, and another is on the infrastructure side. So in order to do that in the code, there are different kind of mechanisms you can do. Hystix was one of the very popular library, which is UL now, end of life. But two of the most important libraries in Java world are Resilience 4J and then Sentinel. So they give you the ability to define your application's alternate behavior in case of a failure, in case of exception. And from there, you can easily configure like what kind of flow you want to do. In this case, what happens is you need to embed these libraries into your code. So there are different kind of libraries available into different languages. But again, you need to, in order to leverage that, you need to instrument that into your code itself. You need to inject those libraries into your code. So that is an extra hop you need to do. So that is why there is a second kind of circuit breaker implementation where these proxy pattern comes into picture along with circuit breaker. And Istio and Envoy gives you the very good ability to do that, the same thing. Essentially, in the Istio world, they inject a sidecar, and then sidecar keeps track of inbound and egress and ingress traffic for your container. So from there also, you can apply this kind of behavior where if you need to turn off the traffic to a particular container and then you need to redirect that to some other container. So Istio also gives you that. So the leverage of that is you don't need to do anything, any instrumentation with your code. You can handle totally it at the infrastructure side. So that is where the circuit breaker comes into picture. Now, well-defined SLXs. So that SLX essentially talks about service level objectives and service level indicators in your distributed system. So anytime you are integrating with any system and you have a dependency, you should always have the indicators and objectives defined. Like how do you measure if a system is behaving correctly? and what kind of indicators or what kind of KPIs you need to measure in order to determine whether the system is behaving correctly or not. So, for example, if you are integrating with a particular system, you should essentially, ideally, in the microservice world, there is this notion of red matrix where you measure request rate, error rate, and durability and things like that, which gives you some sense like how your system is performing. If you are sending a request response kind of system, then you can measure the error rate and things like that in order to determine whether your system is behaving correctly or not. So you should, as a practice, you should always do that. And in this case, if you have defined these SLXs like well, then what happens is you can tweak your alerts. So in my experience, I have seen like tweaking the alert definition dynamically. So essentially you have basic indicators defined. Essentially you have basic indicators defined, and then you are measuring those and you are tweaking your alert definition based on to that. And then you need to always validate your alerts as well, because if your alerts, if your SLXs are tweaking, then you need to validate whether your alerts are incorporating the SLXs or not. And smart and actionable alerts. So all alerts should be actionable. If you have any kind of indicators there, then you can tweak your alert definition based on to that. So what did we learn? Essentially, we learn a couple of important concepts, and I have a demo also, which I'll be sharing at the end of this talk. Essentially, I would like to run that demo, but we ran out of time. So feel free to run that, and if you have any questions, reach out to me. So essentially, what we learn is logging information is important. And then architecture consists of components, and any component can go wrong at any time. Call graphs and integration and communication patterns should be traceable at any given point of time. You should be aware about what is going on in your system. And then service level notation should be part of the design. That is, when you are designing an integration pattern, at that time only you should be thinking about your service level objectives and service level indicators. That is how you will define that correct dependency and the accurate dependency, whether the dependent system is behaving correctly or not. So appropriate indicators needs to be defined. I have included a couple of resources. You have, essentially these resources are talking about the structured logging, how to do that, and then microservices, how to debug it. And I have included this demo also. Feel free to clone it and run it. This has all the information and concepts which we have talked about. So yeah, that's all from my side. Thank you so much. Again, if you have any questions, reach out to me on Twitter or LinkedIn as well. So I'll be happy to answer. Thank you so much.